we were looking at, remember, we were looking at analyzing an absolute value function. Kind of a tough one, because we have an absolute value of a quadratic expression, right? And so we had just started this one up. We've done quite a bit of work, right? We wrote this, first of all, we wrote this as a piecewise function. And then we know that in general, the absolute value of A is equal to A wherever the argument of the absolute value, wherever A is positive, and it equals the opposite of A wherever A is negative. And so, we know that the absolute value of x squared plus x minus 6, then, well, we know what it needs to look like. It's going to look like itself wherever that expression is positive valued, and its opposite wherever that expression is negative valued, right? And so we had to figure out, well, where is that? So we looked into solving this. We had to solve this inequality. Where is x squared plus x minus 6 greater than 0, right? And what did we end up getting for this? We ended up getting, we did this couple ways, I think, didn't we? Didn't we? You guys came up with a good way of doing this. We used, I know what we did. Yeah, okay, so we used a table, first of all, right? We just made a little small table for this. And we looked at this expression, x squared plus x minus 6. The zeros of that are at -3 and 2, right? And then we just picked some test values around the 0. So when we plug in a 0, we got an answer, we got a negative result, right? So we know that the function is going to be negative valued between those zeros. And then when we picked test values less than -3 or greater than 2, we found out that the value of this expression was positive. Okay, so that's one way to do it, right? You could sort of, I don't want to spend too much time on this, but I think this is kind of a cool problem to flesh out here, to look at this thing in different ways and just try to see how they all come together. So another way we could think about that is we could make like a little graphic organizer. So we factored x squared plus x minus 6 factors into x plus 3 times x minus 2, right? So we could even do something like, oops, darn it, I forgot, I gotta do one thing here, hang on. We could make like we'll just look at the signs of each of those factors and then the product of those factors. I'll show you what I mean. This is kind of you might have done this last year in pre-calculus. I know we looked at this once in Algebra 2 a couple years ago. So something like this, right? If we were going to look at those factors, the signs of those factors, and again, they were x plus 3, x minus 2. And then the product of those. You'll see that this is the same as our table that we built. If we were to look at we'll just make a number line here. The zeros are -3 and +2. And maybe let's color code this thing. So this one will make green. And so what did I do? Green, oh, there we go. Okay. So then, what would be the signs of the orange factor, x plus 3? Well, x plus 3 is going to be negative every place less than -3, right? And positive every place greater than -3, x equals -3. Okay, what about x minus 2? Well, x minus 2 is going to transition at 2. It's going to be negative for any value of x less than 2. And positive for any value greater than negative 2. And so then what about the product of the two? Well, the product of the two would just be the product of those two factors would be the products of the signs of the two factors. So negative times negative would be positive. Positive times positive is positive. Negative times positive is negative. So we could get at that a number of different ways, but either way it summarizes the table. And then I couldn't resist doing this using completing the square. I thought this was kind of cool. So if we were to complete the square on the left side of this inequality, so we push the 6 over to the other side and we complete the square, we get the result that x plus 1/2 quantity squared is greater than 25/4. If we solve this thing by square rooting both sides, we get the absolute value of x plus 1/2 is greater than 5/2. And we know what to do with that. If we have an absolute value of an expression is greater than a number, remember from clear back in Algebra 2 and last year in pre-calculus, we know that we can replace that with the compound inequality. The argument of the absolute value, whatever's inside, either has to be greater than the positive or less than the negative. And if we solve this, what do you know? We end up getting the result that our absolute value expression is positive whenever x is greater than 2 or less than -3, which again corresponds to our table, right? That's our table. And then we could surmise from that the quadratic expression would be less than 0 everywhere else, which would just be between -3 and +2. Okay? All right, so give me a 1 to 5 on that. Does that all make sense? Okay. Okay, and it's, we did that like 4 different ways. We didn't really have to do that 4 different ways. Remember what our goal was. We just needed to know when we write our function as a piecewise function, we just needed to know where is x squared plus x minus 6 positive and where is it negative. Oh, and another way we could do this too. Well, a 5th way. Another way we could do this is if we were just to graph the quadratic, if we graphed x squared plus x minus 6. Right? Think of what a graph would be. This might even be the easiest way, which is the same thing as f of x equals x plus 3 times x minus 2. Right? Think about what that graph would look like. We have x-intercepts at -3 and +2, right? And a is 1. So the graph opens up, doesn't it? Right? The parabola opens up. So we know that this parabola is going to be positive valued for values of x greater than 2 or less than -3, and it's negative valued in between. So there's, all these, an embarrassment of riches there. All these different ways we could solve that problem. Either way, we come up with this is our piecewise function, and that's our goal here. Whenever we're dealing with an absolute value function in calculus or beyond, if we want to do analysis on an absolute value function, we always want to replace it with a piecewise function. So we did that. Okay, now it makes it easy to differentiate. When I take the derivative of my piecewise function, I'm just going to differentiate each piece separately, right? So we end up with the derivative of x squared plus x minus 6 is just 2x plus 1, and that's on our domain up here where the absolute value, what's inside, is positive. If we differentiate its opposite down here, we just get negative 2x minus 1. And once again, that's just on the other part of the domain between negative 3 and 2. But now the question is, what's going on at 0, right? What's going on where the function has a 0 value, which is in between? Okay, well, how do we do that? How are we going to evaluate the derivative of the function at x equals negative 3 and 2? You can't evaluate a derivative at a single place, right? So what we've got to do here is we have to see if where those top and bottom pieces in our piecewise function, where they join, the derivative would exist if there's not a sharp corner, but if there is a sharp corner or a break in the function or something like that, then the derivative would not exist. Okay? So how are we going to determine that then? If I want to know if the derivative exists at x equals negative 3 or 2, what are the questions I have to ask the math gods here? Think about the cases in which the derivative would not exist. It would not exist if there is a break in the function, if it's discontinuous, right? Remember to our previous discussions, differentiability implies continuity, right? So a function must be continuous to be differentiable, okay? How would we determine if the function is continuous? If it's continuous at negative 3 and 2, what would we do?
Take the limit of one of the other functions there. So the function, take the limit of the original function there?
Yeah, right. So we have to know that the limit exists. If the limit exists from the left and the right at each of those x values at negative 3 and at 2, then we know that the function is continuous. Everybody agree? Think what a limit means. For the limit to exist, the ants approaching from opposite sides have to agree at where they think they're going to step, right? Okay, and the function is defined. The value of the function at negative 3 and at 2 is 0. So we just have to know if the ants both anticipate stepping on 0 as they approach from the left and the right at each of those values, negative 3 and 2, right? So this is really a good problem. I mean, this stitches together so much stuff that we've talked about. So I'm going to make a new page here, and we're answering the question, first of all, is the function, we'll just say it is f of x. Right? To answer that question, we're going to take limits. Okay, if it's true, that's true. The limit of f of x as x approaches negative 3 from the left must equal the limit of f of x as x approaches negative 3 from the right, and the limit of f of x as x approaches 2 from the left must equal the limit of f of x as x approaches 2 from the right. Okay, well, we can check that. Let's look at the limit. We've got this thing in factored form. Let's take those limits. So what is the limit of f of x as x approaches negative 3? Oops, we got to write it as piecewise. What am I doing? We got to write it as piecewise function. Let me take a picture of this from the previous page. So here's our function written as a piecewise function, right? Okay, so there's our function. What is the limit as x approaches -3 from the left? So as we're approaching -3 from the left, are we in the top piece or the bottom piece? Type your answer in chat. If we're approaching -3 from the left in our piecewise function, are we on the top piece or the bottom piece? Give me a T or a B. Everybody. Okay, good. I'm seeing lots of T's. Yeah, that's right. Okay. Approaching -3 from the left, we would be in this part of our domain of the top function, right? So then what's that going to give me? If I approach -3 from the left, I'm going to be evaluating the top piece of the function. If I let x approach -3, what do I get? Well, that's going to give me 9 minus 3 minus 6. I get 0, don't I? What if I approach f of x, or if I approach -3 from the right? Approaching from the right, I would be in this domain, right? I'd be in the domain where x is greater than -3 and less than 2. So I'd be in the bottom piece. If I evaluate the limit of the bottom piece at -3, once again, I'm just getting negative the quantity 9 minus 3 minus 6. I get -0, which is 0. Okay, so that checks out, doesn't it? Yeah, we knew it would. Okay, so that checks out. What about at 2? If I'm approaching 2 from the left in my function, give me a T or a B. Am I in the top or the bottom? If I'm approaching 2 from the left in my piecewise function, am I top piece or bottom piece? Okay, good. I'm bottom piece, aren't I? Good. So if I evaluate the bottom piece at x as x approaches 2 from the left, I'm going to get negative the quantity 4 plus 2 is 6 minus 6, I get 0. If I approach 2 from the right, I'd be on the top piece. And what am I going to get? Well, I'm going to get 0, aren't I? If I evaluate this top expression as x approaches 2, once again, I just get 6 minus 6 is 0. So it checks out. Okay, so we know that the function is continuous. Okay, good. But just because it's continuous, does that mean it's differentiable? No. Differentiability implies continuity, but we can have functions that are continuous and not differentiable. That would be the case if there were a sharp corner. Okay, so the next issue we have to address is, let's make another page here. So here's my question. Is there a sharp corner at x equals -3 or x equals 2? Because that's the other instance where our derivative would not exist there, right? Okay, how am I going to answer that one? Think about that for a second. How in the world am I going to answer that one? Is there a sharp corner at x equals -3 or x equals 2? Okay, don't say anything, but everybody think about that for a second. I'm going to give you a hint. I have to go back and copy something anyway. So here's what I'm copying this time. I'm copying my derivative function, okay? And let me erase this part in the middle, though. We don't know if the derivative, I kind of jumped the gun on this. I didn't give us adequate time. We don't know what's going on here yet. Right, at x equals 2 or x equals -3. We don't know. That's what we're trying to find out. If the derivative exists there. And if so, what's the value? Okay. Any ideas? Kyle, what do you think? You got an idea there? How I could determine if there's a sharp corner at x equals -3, let's say?
I don't really know.
Okay. Andy, you got an idea?
Is it something with taking the derivative? I don't know.
Okay, yeah. Okay, that gets a start. Madeline, you got an idea?
Do you like take the limit on either, like how you did for the first one, like on either side of the derivative?
Ah, there you go, right? So we want to find what is the derivative at -3 from the left and from the right, which means we're taking the limit of the derivative function as x approaches -3 from the left or the right. And then the same thing for 2, right? Everybody agree? So we want to know here, here's our question. Is the derivative from the left, and we'll do this at x equals -3, is the derivative from the left equal to derivative from the right at x equals -3? That's the question. Well, the derivative from the left is just going to be the limit of my derivative function, right? If I'm approaching -3 from the left, as x approaches -3 from the left, my top or bottom piece of my derivative function. -3 from the left, that's going to be top, isn't it? Right? Because that's going to be between -infinity and -3. Okay? So we're taking the limit of 2x plus 1 as x approaches -3 from the left. Well, what's that give us? That's an easy one to evaluate. That's just equal to -5, right? If I let x approach -3, I get -6 plus 1. I get -5. So the derivative from the right as x approaches -3, that's going to be my limit as x approaches the right. Well, that's between -3 and 2. I'm approaching from values between -3 and 2. So that's in the bottom, taking the limit of -2x minus 1 as x approaches -3. And that's giving me 6 minus 1, which is 5. Well, look, those are not equal, are they? Right? So what's that mean? The derivative from the left is -5. The derivative from the right is 5 at -3. And so what can you tell me about the derivative, everybody, at -3? Does it exist? No, right? It's a sharp corner. I get differing values of the derivative as I approach -3 from opposite directions, right? And then I won't take you through the whole exercise, but we could do the same thing. If I do the same thing for x equals 2, we're going to get the same result, aren't we? Right? Okay, so then we know that if we go back to our piecewise derivative function, that the derivative is undefined. At 2 and at -3, right? Okay, so now we have enough information that we could actually make a table out of this thing. Okay, so let's copy all this stuff, and we could even do a second derivative if we wanted to. That's pretty simple. We'll do that. Okay, so there's our first derivative, or there's our function, our first derivative. Let's go ahead and take our second derivative too. I'll just put it over here so we can save a little space. As a piecewise function, what am I going to get for the top piece of my piecewise function? Type it in chat for my second derivative. Okay, good. Getting second derivative equals 2 on my top domain. Bottom one would obviously be -2, right? And if the first derivative is undefined, well, the second derivative has to be undefined at 2 and -3. Okay, so let's make our table then. What do we find? So our first derivative, are there any places here where our first derivative is equal to 0? Okay, well, we'd have to look at both pieces, wouldn't we? What about that top piece? At what value of x is that top piece equal to 0? Type it in chat. Okay, -1/2. So is that a critical number then? Yes or no? Okay, give me just a y or an n in there. Okay, I'm going to stop you right there. The answer is no, but how come? What's wrong with it? It's not in the domain, is it? Yeah, look, the top piece up here, so I'm just going to color code this. So this top piece up here, the critical number for that piece is x equals -1/2, but is -1/2 in the domain of that piece? No, right? -1/2 is not less than -3, and it's not greater than 2. So that's not a critical number, right? What about the 0 of the bottom piece? The bottom piece is 0 at -1/2, isn't it? Everybody agree? If I set the bottom equal to 0, would you guys all agree that this bottom piece, my critical number, is x equals -1/2? Give me a thumbs up. You guys agree with that? Okay. That one works, doesn't it? That one works because that is in the domain of the bottom function. Everybody agree? So -1/2 does end up being a critical number. So technically you were right. I just don't think you guys were right for the right reason if you said yes. So we get -1/2 is a critical number. It's where y prime is equal to 0, okay? Because we have to be in this part of the domain, right? That works. What other critical numbers did we get? Type them in chat. What other critical numbers? Remember, critical numbers exist where the derivative is equal to 0 or where it's undefined, right? Okay, good. So we get -3 and 2 then, don't we? Because that's where my derivative is undefined. Okay, so -3, +2. Our first derivative is undefined. Okay, and what do we know about our second derivative? Okay, our second derivative, well, we know that at -1/2, our second derivative is negative, right? Hang on. -1/2. Yeah, our second derivative is negative. Okay? Right? If we look up here. So what's that telling us then? That's telling us we've got a horizontal tangent line. And, oops, why'd I put a positive? I said negative. And our function is negative, so it's concave down. So that's got to be a smooth maximum. How am I going to know what's going on here? What should I do here? At those other critical numbers, what are some suggestions? What could I do?
Has points on either side. Well, I mean, we know from the graph that it's a parabola on the outside, so it's going to have to come down.
Okay. Okay, good. But let's pretend it was a more complicated graph. You're right about that. So I'm going to have to have some test points there, don't I? Right? Because the second derivative test cannot be applied at x equals -3 and +2 because the second derivative test only works for 0 first derivatives, right? Where it's undefined, if the derivative is undefined, there obviously can't be a concavity there, right? So we would either have to go back to the first derivative test. Let's do that because that's the general rule in calculus. We always say when the second derivative test fails, you revert to the first derivative test. So let's do that. Let's pick test points surrounding -3. Like what if we pick between -3 and -1/2? So we could pick like -2 and -4. And then up here, we could pick between -1/2 and 2, we could pick like 0, how about, and 3, okay? We could evaluate the signs of the first derivative there. What's the sign of our first derivative at -4, everybody? Look at our piecewise function for our derivative function. What's the sign of the first derivative at -4? Okay, good. So we're at -4, we'd be in the top piece, wouldn't we? So if I'm plugging in, if I evaluate the top piece at -4, I'm going to get a negative result, aren't I? So we know that it's negative there. How about at negative, I can't, 2, oh yeah, I can, at -2. How about at -2? Give me the sign of the derivative there. What's the sign of the first derivative at x equals -2? So you got to figure out which row are you in, or which piece, top or bottom are you in, right? And then go from there. So at -2, that would be between -3 and +2. So we're in the bottom piece. If I evaluate the bottom piece of the derivative at -2, I'm going to get +4 minus 1. That's positive. Okay, so that tells us something then, right? We know that if we have an undefined first derivative, so it's a sharp corner and we're going from negative to positive, we know that this is going to be a minimum, isn't it? It's a sharp minimum, okay? How about over here? If we try it at 0, we can go quickly for this one. So at 0, that would be in the bottom piece, wouldn't it? If I plug 0 in for x, I'm going to get a negative result. At 3, we'd be in the top piece. If I plug 3 in, I get a positive first derivative. And look what we know about the second derivative while we're at it here. We know that at -4, the top piece would be positive. It's 2, right? At -2, we'd be down here, so we get a negative second derivative. At 0, we get a negative second derivative. We're in the bottom piece. And at 3, we're in the top piece where we get a positive second derivative. So that gives us pretty much everything we need. It gives us the exact shape of these, of what these must be, right? We know that we have a positive concavity and a negative slope. So that's looking like that, right? We got our sharp corner. We got our sharp corner here, and then we get a positive slope and a negative concavity. Okay, so that's going to look like that. So there's what this minimum looks like. Here we got a sharp corner going from decreasing to increasing again. We're going negative slope, negative concavity. So that looks like this. Here we get positive slope, positive concavity. It looks like that. Right? So if we knit all that stuff together, what does this function have to look like? So here's 0, that's our x or y-axis. Okay, we had at the point -1/2, what? What's our function at -1/2 if we plug that in? What's that going to be? -1/4 minus, so negative, so it's going to be 6 1/4, so 25/4. At -1/2, 25/4. -1/2, 25/4. So up here somewhere, we've got a smooth maximum at -3, 0. We know we've got a sharp minimum that looks like this, right? So our function's coming down. I mean, this is not drawn to scale at all, right? And then on the other side, we're going to get the opposite going on, aren't we? Out here at 2, 0. So out here, we've got something like that going on. So we got our function. That's a tough one. That's really tough. You know, dealing with an absolute value function like that, that's not a linear absolute value function. There's a lot going on that one. So what's this tell us about absolute value functions? If we graph this thing, you tell me, how would you describe what's going on? Yeah. So if I graph this, f of x equals the absolute value of x squared plus x minus 6. Yeah, look what happens, right? If we compare that to the function f of x equals just x squared, I will call it g of x, g of x equals x squared plus x minus 6, look what happens, right? What's it do? It just bounces off the x-axis, doesn't it? Doesn't that make sense? Because what's the job of an absolute value function? It's to make negative output values, negative y values positive. So in effect, when you think about an absolute value function, you can always just think about it as bouncing off of the x-axis, and you're essentially reflecting all the negative parts, the parts that would drop below the x-axis up above the x-axis. That's pretty handy, huh? And so now we can see if when that happens, of course, you're going to get sharp corners where it bounces. Okay. All right, give me a 1 to 5 on that. And I wouldn't expect anybody to have a 5. I mean, there's a lot of moving parts on that. But having seen that, I promise you that's going to be helpful someday when you see that again. Okay. I think did I give you one of those on the problem set? Did I give you an absolute value function like that? I can't remember. On the second one, I might have. I can't remember. All right. Last couple, and then we've so thoroughly looked at this stuff that we don't have to look at it anymore for a while. What you're going to find also, the next big topic we're going to look at is called optimization. Super fun. I can't wait to teach it. We'll do it after we get back from spring break. It's taking real applications and using all the stuff we've learned here about functional analysis to find interesting things that are going on with real world functions, right? So where are these functions minimized and maximized? Where might you have points of inflection? Things like that. There's all kinds of economic applications, physics applications. The good news is I have so thoroughly overdone this analysis part that the functions end up being much, much easier than what you've done on this assignment, right? You guys have done, like, I really overdid it on the curve sketching stuff just to get you lots of practice on that. But in reality, you don't oftentimes see functions that are that difficult when you do optimization problems. Okay, so just round this out here. What about this guy? Let's see if we can zip through this. We can have time, I'm hoping. Oh, no chance. We're out of here in 2 minutes. Okay, let's at least take the derivatives. And then I think this will work out fine, actually, because I don't want to start optimization until after break. So we can, we've got this last one, and then I wanted to do one more with a trig function. And then I think that's every possible base we could conceivably need to hit on this. So we'll finish that this week. You guys can be wrapping up, finishing those assignments. And then we'll come back after spring break and we'll hit a new topic then. That's a good time for us to start something new. All right, so our derivatives. Andrew, what's my first derivative going to be for this guy?
So we got 2 and negative 1/3.
So 2x to the negative 1/3. Okay, good.
And then 2x.
Minus 2x. Okay, and if I wanted to, I could write that as 2 over x to the 1/3 minus 2x if I chose to. Okay, while you're at it, give me a second derivative.
Then you got, was that negative 4/3, or, oh God, you have to do some fraction math there.
Well, that's all right though. It's negative 1/3 times 2. What's that? That?
Oh, yeah.
There we go. Okay, x to what power? There you go. X to what power?
And then negative 4/3.
There you go. Negative 4/3.
And then just 2.
Minus 2. Good. Okay. Okay, good. So we're just going to have to find critical numbers. So we're going to ask ourselves, first of all, what's the domain of this thing? We need to know the domain. Okay, we're going to go here. But the fact that that is an odd root, what's that telling us? Do we have problems with odd roots? Right? We can't take an even root of a negative number, right? But we can take an odd root of anything, right? The cube root of -8 is -2. So the fact that that's an odd root means that we don't have anything to worry about. The domain is all reals. We'll leave it there.